Okay, a couple of reminders. These formulas are on your formula sheet, which should be out at all times in this unit. Okay, but we've got that work is a change in energy. Okay, that kinetic energy is 1/2 mv squared, and potential energy is m times g times h. Okay, and change in energy is obviously final energy minus initial energy. That should be enough to get you started. Okay, remember from yesterday, the first thing we want to do is write down our givens, then identify what kind of energy is being changed, then we can put in our formulas, manipulate, and solve. All right, so on this one here, like we want to do with any problem-solving question, is we want to write down our givens. Okay, a tractor pushes a rock, and it's telling us the mass of the rock is 550 kilograms. Okay, so I got mass. That's pretty important when we're talking about work and energy. Okay, from rest to a speed of 4 meters per second. Okay, so from rest is, okay, but which given is that? Initial velocity, right, or initial speed in this case. Okay, 0 meters per second. Okay, and then our final speed would be 4 meters per second. Okay, over a distance of 25 meters. That would be D, yeah, distance. Okay. All right, what is the force being exerted? Okay, so I have distance and I'm looking for force, so I know I'm definitely going to be using force times distance in this question. All right, what kind of energy is being changed here? Kinetic or potential? Kinetic. The speed is changing. Anytime you're given a change in speed, you are changing the kinetic energy of the object. Okay, so we would start out after our givens with this. Work is the change in energy. In this case, kinetic energy. All right, now that I've got that, now I want to expand this out. Work can be calculated by multiplying force times distance. I'm looking for force. I was given distance. Okay, and then change in kinetic energy would be 1/2 mv final squared. That would be my final kinetic energy. Okay, and I'm going to go minus my initial kinetic energy. Okay, so minus 1/2 mv initial squared. Okay, so I've written the same thing almost 3 different ways here. I've written work is delta EK, and then I wrote underneath that delta EK means final minus initial, because delta always means final minus initial. And then I expanded it out to include all the formulas. I put in force times distance for work, and I put in 1/2 mvf squared, that's how we calculate kinetic energy, okay, minus the other kinetic energy. All right, I've just written the same thing 3 times. Everybody with me so far? Okay. Since VI is 0, what is 1/2 mvi squared? 0. So can I get rid of it? Okay. Subtracting 0 doesn't do anything. Okay, so I'm going to get rid of that. Not what I want. All right, so now I'm down to this. Force times distance equals 1/2 mv final squared. I have V final, I have D, I have mass. I've got everything but force, and force is what they want me to find. How do I get force by itself? Divide by D. Yeah, move D over to the other side. Okay, so now I've done my algebra. Okay, the D is gone there, and I'm solving for force. Now I can plug in my numbers. Okay, force equals 1/2 times 550 kilograms times 4 meters per second, all squared, okay, divided by 25 meters. All right, so 0.5 times 550 times 4 squared, okay, divide that by 25 meters. Okay, so 176 newtons worth of force was used to push the rock. Okay? getting a few side eyes. What's going on, guys? Where did I lose you? It's okay to say you're lost. Just gotta tell me where. Okay. The pattern is always going to be the same. Okay, that's what we have to understand. Every time we do this, we're going to write our givens. We're going to use our givens to determine whether potential energy is changing. We'll know that if there's a change in height. Okay, or if kinetic energy is changing, like in this question where there was a change in speed. Okay, then we can go work is a change in either kinetic or a change in potential energy. Right? Then we just expand. Force times distance equals final minus initial. Okay, manipulate, solve. It's always the same pattern. Okay, it's why we're going to spend so much time doing questions like this, so that once you learn the pattern, you realize these are all kind of the same. Okay. All right, we did that one yesterday. Okay, let's have you try this one. This one's a little bit trickier, but still the same pattern. Okay, the answer is there in blue. Okay, so if you get 3.16 meters per second, you did it right. Okay, just in case you're stuck kind of getting started, I'm just going to go through the first two steps. Okay, so we know that the bulldozer does 7,500 joules of work. So they actually tell us how much work is done, which means I'm not going to need to do force times distance here. They already told me what that equals, 7,500 joules. Okay, and that's in pushing a truck, okay, from a speed of 2 meters per second. So if it's from 2, that would be the initial, to an unknown velocity. Okay, so VF is unknown here. The truck has a mass of 2,500 kilograms. Okay, what is its final velocity? All right, so there's the stuff I know. Those are my givens. What kind of energy is being changed by the work? Kinetic. The speed is changing. Okay, so work is a change in kinetic energy. So that means since I have work, I don't need to put in the force times distance part. Okay, final kinetic minus the initial kinetic. Okay, I'm gonna stop there and then see if you guys can take it from there. Right, you have the formula on your formula sheet for kinetic energy. Okay, my suggestion would be figure out which one of these two things VF would be in and isolate that before you put in the formulas. So the question wants us to find the final speed of the truck. Okay, now final speed would be part of final kinetic or initial kinetic? It's the same thing here. I can use those, I shouldn't, but I did use those terms interchangeably. Okay, there's not going to be a direction on this because it is going to be speed. I wrote velocity, but I should have wrote speed, so good catch. Yeah. Okay, so which would it be part of? Final kinetic or initial kinetic if I'm looking for final speed? Final, yeah, I mean they go together, right? We put final speed when we calculate final kinetic energy. So what I'm looking for is part of this term. So I want to get that term by itself before I put a whole bunch of other letters and stuff in there. So how do I get EK over to the other, EK initial, sorry, over to the other side? Add it, right? Right now I'm subtracting it, so I would add it to the other side. So the change in energy, the work, plus the initial kinetic energy should equal the final kinetic energy. Okay, that kind of makes sense when you say it in your head, right? The change plus the initial would give me the final. Now, I can put in my formulas. Okay, this number I know, so I don't need to put a formula in for that. I know it's 7,500 joules, plus 1/2 times mass times initial speed squared. That's my initial kinetic energy. that's going to equal my final kinetic energy, which is 1/2 mv final squared. Okay, still the same pattern? It is. I mean, I'm solving for something different, but I'm still doing the same steps. I wrote my givens, I identified the type of energy that was being changed, and then I started isolating whatever it was they wanted me to find. That's kind of the biggest step, okay, in terms of the amount of work. The most important step is actually identifying the energy being changed. Now that I've got this, okay, I need to isolate VF. How do I get VF by itself? Divide the 1/2 and m over to the other side because they're being multiplied. Okay, that solves for VF squared. I just want VF. What do I have to do? Square root. All right, so now I can plug in the rest of my numbers. Okay, so VF is going to equal the square root of 7,500 plus 1/2 times 2,500 times 2 squared divided by 1/2 times 2,500. Now, sometimes people say, Mr. Coderre, couldn't you just cancel that? It's the same on the top and the bottom. The answer to that is no. You're adding up here. If everything up top was being multiplied, absolutely you could, but you have an addition or subtraction operation, so you can't. Okay? All right, so now if we plug in our numbers here, okay, into our calculator, okay, we'll go 7,500 plus 0.5 times 2,500 times 2 squared. Okay, we'll divide that by 1/2 times 2,500. And we'll square root that. And we get 3.16 meters per second. Okay, now notice I did use some brackets in there. Okay, there is some stuff you have to make sure that you do in order for your calculator to spit out the right answer. Okay, that would be about as tricky as a work energy theorem question would get in Science 10. Okay, and not because the concept is difficult, it was probably pretty straightforward to identify it was kinetic energy, but the algebra is pretty involved in that stuff. Okay, so in case you haven't noticed, you are going to have to flex your algebra muscles a lot, okay, in the remainder of this unit. There is a lot of manipulation that goes on.
How many marks would a question like this?
A question like that would be a 5-mark question, okay? So let's kind of show you where the marks would go. So you would get a mark for your givens, okay, as you always do. You would get a mark for identifying the type of energy that is being changed, okay? You would also get a mark then for setting up your work energy theorem, okay? You would get a mark for your manipulations, okay? What are we up to there? Oh, sorry, I put those in the wrong spot. Okay, sorry, you would get a mark for setting up your manipulations, that's your work energy theorem, okay? Plugging in your numbers would be another mark, and your answer would be the 5th mark. Okay, so givens for 1 mark, identifying the type of energy being changed for the 2nd mark, okay? Your manipulations of the formula, you're plugging into the numbers, your final answer, 5 marks. Okay? All right, questions on that? Guys, it is okay today to feel a little bit intimidated. Most people are the first few days of work energy theorem because of the algebra. Remember, the algebra will come. That just comes with practice. Okay? What I'm most concerned with is, can you read one of these problems and know, okay, that's a kinetic question or that's a potential question. The algebra will come. You guys know how to do algebra. I'm not asking you to do anything nearly as difficult as what you would have done in Math NC. Okay?
Do you have a quiz on Friday?
Yes, that's why I showed the practice quiz a minute ago. Okay. All right, so here's what I would like you guys to do. I want you to write down the steps here, okay, for work energy theorem. Maybe make that like a separate page or something, okay? These are the steps for solving a work energy theorem problem, or the pattern that you want to follow, okay, when solving a work energy theorem problem. So I'll give you a few minutes to copy that. We haven't done, well, one like this for a little while, okay? So I'd like you to copy this one down and give it a try. Still a work energy theorem problem, okay? Not really any different than what we've been doing, okay? Just read it carefully. As you write down your givens, decide what type of energy is being changed, set up work energy theorem, manipulate, and solve, okay? So in this one, you got a heavy box, and you're told it's a 35 kilogram box. It's pushed up a hill using a force of 150 newtons over a distance of 25 meters, okay? How much higher is the box at the top of the hill? Okay, so if you're a visual person, okay, this is what we are looking at. Okay, this is the 25-meter hill, all right? The box is being pushed from the bottom to the top. We want to know, okay, how high above the bottom of the hill is it when it gets to the top? Okay. So our givens for this one are that we know the mass. Okay. Okay, so we know the mass. It's 35 kilograms. Okay. We know the force is 150 newtons, and we know the distance is 25 meters. We also know the initial height of the box. It's never outright stated, but what's your height at the bottom? Right? Okay? So it never outright says that, but it's a context thing, right? I have to get that from the story. Okay? A little reading comp for you in science. Okay? I started at the bottom of the hill. Well, the hidden meaning in that is the height was 0. Okay? I don't know. English works something like that. I don't really understand it. But, okay? So 0 meters would be our initial height, and we are looking for the final height. Okay, so now we've got our givens down, and we see there's a change in height. So what kind of energy is being changed here?
Potential.
Potential energy. Okay, so next step, work is a change in potential energy. Okay, again, just following those steps that you just finished writing down. Work is force times distance. I'm writing that down because I was given the force and the distance. Okay, and I'm going to write here that the change in potential energy is the final minus the initial. But since I start this question at the bottom of the hill, what's my initial potential energy? 0. Okay, so I can get rid of that. Okay, so force times distance equals the final potential energy. Okay, so that means force times distance equals m times g times h final. Okay, so all I did there was plug in the formula for potential energy. Can I now isolate final height? Okay, what do I do with m and g? Divide them over to the other side. Okay, I've manipulated, now I can plug in and solve. All right, so I'll have 150 newtons times 25 meters, force times distance, okay, divided by 35 times g. Okay, remember that g is always 9.81 unless you are told otherwise, which you will basically never be. Okay, all of this stuff is going to occur on Earth. All right, that's going to equal our final height. Plug it in. 150 times 25. All right, and divide that by 35 times 9.81. Okay, so that box will be 10.92 vertical meters above the bottom of the hill, or ramp, or whatever it was. Okay, that one was easier algebraically, wasn't it? Right, because we didn't have any initial energy. Okay, and sometimes it works out that way, where the initial is 0 and everything is hunky-dory and the algebra is easy. Okay, and sometimes it's not, and you have to subtract the energy over. Okay? It's going to depend on what kind of question you're getting. Any questions on what we did there? Yes, but put your phone in the pocket before we go. Okay, questions there? Okay. I'm going to give you guys about a 4 or 5 minute break here, okay, and then we'll try some more, okay? Okay, I want you to give this one a try. The answer is there. The answer is 46.4, so when you're done, you get that number, you did it right. All right, so we know that the mass of the baseball. Okay, so mass is going to be 0.250 kilograms. Okay, and they use 300 newtons worth of force. Okay, over a 0.9 meter path. So that would be the distance. Okay, what will the speed? At what speed will he release the ball? So we're looking for VI or VF? VF. What's VI? 0. Okay? We were having a discussion about this before class started about how boring it is to watch baseball. Okay? That's like 3 hours of 2 guys playing catch. I don't understand. I love the highlights though, because then you see when all the hits get made. So if you're starting as the pitcher, you're sitting there with the ball in your glove, waiting for your signal from the catcher. The initial speed of the ball is 0. It's another one of those context givens as opposed to actual numbers. All right, we just have to understand that before someone throws the ball's not moving. Okay, it's not like somebody threw the ball to you and you kind of caught it and gave it a push as it was flying through the air. Okay, that would be a pretty technical thing to do. Okay, in this case, we're just standing there with the ball and the ball is not moving. Okay. All right, so those are our givens. What kind of energy is being changed? Kinetic. Kinetic's being changed because the speed's changing, right? The ball is being accelerated here. So our work that is being done by the pitcher is going to change the kinetic energy of the ball. Okay? It mentions nothing about him throwing the ball up in the air, okay, or changing the height of the ball. Okay. So now I know that work is changing the kinetic energy. I was told the force and the distance that was used, okay, and that is going to equal the final kinetic energy minus the initial kinetic energy. And since the ball is not moving at the beginning of this, the initial kinetic energy is 0. All right, so now I can say that force times distance equals 1/2 times the mass of the baseball times the final speed of the baseball squared. Okay, everybody all right with that? All right, how do I get VF by itself? Divide by 1/2 of m, right? Okay, so I'll divide 1/2 of m off of this side. What I do to one side, I have to do to the other. That's the rules of algebra. Okay, that's going to solve for VF squared. I just want VF, so what do I have to do? I have to square root. Right, so the square root of force times distance over 1/2 of m will equal VF. And with the numbers plugged in, that'll be 300 newtons times 0.9 meters divided by 1/2 times 0.250 kilograms. Okay, so should actually come up to 46.5, not 46.4 if we round properly. Okay, meters per second. Okay, is that really any different than any of the other ones we've done? No. Okay, again, once you learn the pattern, and the best way to do that is just to practice, okay, you won't have any trouble with these. Okay? It's not like the algebra here is awful, okay, you have to move a couple of things, and if you're solving for V, you got a square root, okay, but there's really nothing super technical about these. Okay, this is just like the very first example we did, where I went on my rant about how important it is to drive 30 kilometers an hour in a playground zone. Okay, so this is very much like that question. Here, they want to know how far does the car travel, okay, in this situation. All right, so on this one here, okay, we know that the car's brakes can apply a force of 10,000 newtons, so force is a given. Okay, and it's going to slow from 20 meters per second to 6.
Negative 10,000.
Oh, yeah. Okay. I was going to address that in just a sec, but you're ahead of me, so I'll put the negative on there. Why is that negative? Yeah, it's stopping. The force has to be backwards. Force is a vector quantity. Energy and work are not, but force is a vector quantity. And if you're going to stop, that force has got to be backwards. If you don't make it negative, then it says you went backwards by applying the brakes. And the last time I checked, and I drive a lot, okay, applying the brakes does not make me go backwards. It makes me accelerate backwards, but never makes me go backwards, which would be a real safety concern. Okay? All right. Which one, 20 or 6? Would be our initial? 20. Okay, and VF would be 6, okay, and that's a context thing. And then if the car's mass is 1,700 kilograms, how far did it travel? So, what kind of energy is being changed here? Kinetic speed is changing. So work is a change in kinetic energy. I was told force, I'm solving for distance, so that'll need to be part of my formula, equals EK final minus EK initial. And in this question, neither one of those is 0, so they both got to stay. Yeah, just put your phone in the pocket first. Okay, so how do I get distance by itself? Divide by force, right? Bring the force over to the other side. All right, so now I've got my manipulations there. I can put in the rest of my formulas. So D is going to equal 1/2 times mass times final speed squared minus 1/2 times mass times initial speed squared divided by force. Then we'll plug in our numbers. 1/2 times 1,700 kilograms times 20 squared minus 1/2 times 1,700 times 6 squared divided by 10,000 newtons. All right, now this is another one where brackets are going to be important.
Isn't 6 and 20 supposed to be switched? Yeah.
Oh, sorry, I had them backwards. You are absolutely right. After I made such a big deal out of which one was initial and which one was final, I messed them up. And we'll square. Okay, good catch. So 0.5 times 1,700 times 6 squared, okay, minus 0.5 times 1,700 times 20 squared. All right, there's where our negative number comes in, right? Because obviously we have less energy at the end than we had at the beginning, okay? So now I'm going to take that and divide by that negative 10,000 newtons. All right, they are going to travel 30.9 meters as they brake. Everyone all right with that one? There's really only so many ways I can ask a work energy theorem question. You've seen them all at this point. Right? I can give you one like this and ask you for final speed, or I can give you one like this and ask for distance, or for force, or initial speed. Like, there's only so many manipulations of this that there can be. And the same is true for one involving potential energy. So like I said, practice makes permanent. Okay? It doesn't make perfect because nobody's ever perfect no matter how much you practice. Okay? But practice makes permanent. Okay? If you practice it, you will get good at it and you will do it the right way each and every time. Okay? Okay, now this one, the context can be a little bit confusing. because the slingshot is being aimed straight up in the air. So we also know with this question, okay? In this question, this height is measured from the ground, and we start on the ground in this question. Okay? It doesn't outright say that, okay? But it is important to know that if we're measuring from the ground, that means our initial height was the ground. Right. All right, let's have a quick look at this one here. So the slingshot is aimed straight upwards, and it says it's drawn back 0.4 meters. Now, in a question like this, that can be confusing because distance and height use the same units. Here's how I can tell that number is distance. It's what I drew back the slingshot. That's not included in the height. That's what I did to do the work. Okay? It was part of the force that I used in order to load the slingshot. Okay? So I have to know in the context of that question that the distance the work is done over is 0.4 meters. Okay? And the force used is 1,500 newtons. All right? The rock reaches a height of 30 meters. That would be its final height. And its initial height, because it's from the ground, is 0 meters. All right? What is the mass of the rock? All right. What kind of energy is being changed here? Potential energy. I mean, there's also kinetic energy being changed, but we're only concerned with the potential part. So work is a change in potential energy. I have force and distance. That's going to be final potential minus initial potential, which is 0 because we're on the ground. Okay, so this comes down to force times distance equals m times g times h final. All I have to do is move m and g to the other side by dividing it. Yeah. Bless you. All right, h final then is going to be 1,500 times 0.4 meters, force times distance, divided by the mass, which was, we're looking for mass. I'm leaving height by itself. Sorry, guys. Getting distracted here. Let me try that again. I'm going to bring g and hf over, m times g times hf, and I'm going to divide both sides byghf. My apologies. Okay, so that's going to be 1,500 times 0.4 divided by 9.81 times 30 meters. Okay, when we do that, we should get the mass of the rock. So 1,500 times 0.4 divided by 9.81 times 30. Okay, it's a 2 kilogram rock. That is a big rock. Okay, you would not want to get hit by a 2 kilogram rock. Not that you want to get hit by any rock, but a 2 kilogram rock especially would really, really hurt. And one that fell from 30 meters would be going really, really fast. Okay. All right, questions on that? Your quiz tomorrow has 3 acceleration problems and 2 work energy theorem problems, and they are exactly like the ones we have gone over today, not the hardest ones I could think of. Okay? They have a nice, interesting story, interesting in air quotes, story to go along with them, okay? But they're not mathematically difficult.